Hello, everyone. My name is Ao Shi, and I'm a PhD student in Professor Joshua Lewis Group at University of California, Riverside. Today, I'm going to present a talk I was giving at the APS March Meeting 2023. The title of my talk is Electric-Field-Tunable, Type 1 to Type 2 band transition in molybdenum diselenide and tungsten disulfide heterobilayer. So to begin with, I'd like to introduce different types of band alignment. So for semiconductor heterostructures, their properties depend crucially on the types of band alignment between the two materials. So generally, depending on the band configurations, these band alignments can be classified into several different types. So the first one here is the type 1 band alignment. So in this band alignment, the conduction band minimum and the valence band maximum are lying in the same materials. So the charge carriers are excited in this case will be relaxed to the same materials and be confined there. So such strong confinement of electron and holes basically enhances the overlap between their wave functions, which makes this type of band alignment suitable in applications such as light emitting devices or field effect transistors where high mobility are required. So another type of band alignment is called the type 2 band alignment. So in this band alignment, the conduction band minimum and the valence band maximum are actually lying in two different materials. So the charge carriers excited in the case will be relaxed to two different materials and be dissociated from each other. So such dissociation of electron and holes basically makes this type of band alignment suitable for applications such as photodetection or photoelectricities. So there are many different heterostructures. They can belong to different types of band alignment, but for each heterostructure, generally they only belong to either one type of band alignment or the other type. For example, the famous example here, the aluminum gallium arsenide and gallium arsenide semiconductor heterostructure, it can actually be grown with very high mobility and be frequently used in fundamental studies such as fractional quantum Hall effect. This heterostructure actually is a type 1 band alignment heterostructure. So the conduction band minimum and the valence band maximum lies in the gallium arsenide layer, while the aluminum gallium layer has a slightly larger band gap. So for charge carriers injected into such heterobilayer, it's actually confined in the gallium arsenide layer. This actually makes them stay away from any impurities or disorders and actually enhances the carrier mobilities of such materials, which makes them suitable for studies such as fractional quantum Hall effect. So some of the recent examples include the Van der Waals heterostructures made by different two-dimensional materials. So here I show examples such as MoSe2 and WS2 heterobilayer, or the WS2 and W heterobilayer. They actually both belong to type 2 band alignment, meaning that electron and holes generated in these systems will relax to two different layers. So they bound together to form a new type of exciton called the interlayer exciton, which was recently studied a lot and been shown to be an interesting probe of many interesting states in the systems. So for most of these materials, their band alignments are generally fixed. So the question we want to ask in our research is, can we find a heterostructure where we can tune the band alignment, for example, from type 1 to type 2? And that's what my study today is about. So to achieve this, basically, we study the MoSe2 and the WS2 heterobilayer. So here we show our device schematic. Basically, we encapsulate our heterobilayer with boron nitride, and then we put graphite both on top and on the bottom of the device. So we basically make a dual gate structured device. So such dual gate samples actually are very important for us because it allows us to basically control the charge carrier density in the system or the electric field independently. So the experiment we do is the photoluminescence spectroscopy measurement. We basically perform the PL studies at the lowest temperature in our cluster, which is about 6 Kelvin. And then we vary the gate voltages and measure the PL spectrum at these different gate voltages. So first, we show our charge density dependent PL map. So in this map, basically we apply the same gate voltage to both the top and the bottom graphite gate. So then only the charge carrier density in our system is changed, while the vertical electric field is kept at 0. So basically, we show the PL spectrum at different photon energies as a function of these different gate voltages. So basically, we can divide our map into 3 different regions. So close to the 0 volts gate voltage, basically the heterostructure is in the charge neutral regime. So in this regime, we actually observe a bright luminescence peak here, which actually has energy about 1.60 eV. And then when we increase the gate voltage or decrease the gate voltages, we basically enter the electron-doped regime or hole-doped regime. And we found that in these 2 regimes, this bright luminescence peak disappears, and we observe 2 side peaks, and their energies are slightly lower than this bright luminescence peak. So basically, these behaviors are consistent with the typical trion and exton behavior in a monolayer semiconductor. Basically, in the charge neutral regime, the Fermi level lies midway between the conduction band minimum and the valence band maximum of the materials. And then the electron and hole injected into the system will bond together to form an exciton. And this recombination of the exciton basically results in the luminescence peak, as is what we observed in the PL map. But importantly, when we check the energy of this exciton luminescence peak, it's about 1.60 eV, and it's actually close to the MoSe2 excitonic gap, which is 1.65 eV, and it's far away from the WS2 excitonic gap. So this means that this excitonic peak here is entirely coming from the MoSe2 layer and has nothing to do with the WS2 layer in our heterostructure. So when we dope the system, we essentially move the Fermi energy either up into the conduction band or low into the valence band. And these additional injected charge carriers, either electrons and holes, will bond with the excitons to form the trions, which results in the 2 side peaks we observed in our PL map with slightly lower energy. But also importantly, when we measure the energy difference between the side peaks and the neutral exciton peak, we essentially found the trion band energy, which is about 30 millieV. And it's also close to the MoSe2 trion band energy. So this means that the entire trions and excitons we observed in this map basically are coming from the MoSe2 layer. And the system actually is a type 1 band alignment system. So next, we perform the electric field dependent PL measurement. So in this map, we basically apply the opposite gate voltage to the top and bottom graphite gate. So in this case, we only induce a vertical electric field across the heterobilayer while keeping the charge density in the system to be 0. So what we observe here is at 0 or low electric field, the excitonic peak we previously observed in the charge density PL map actually has no electric field dependence. So this actually further confirms it's an intralayer exciton coming from the MoSe2 layer, because for an intralayer exciton, the electron and holes are sitting in the same layer. It has no out-of-plane dipole moment, so it does not couple with the electric field. But when we increase the gate voltage toward the positive side, we have an electric field pointing from the WS2 to the MoSe2 layer. And what we found is that there's actually a new luminescence peak showing up in our PL map. And it actually has a strong electric field dependence. So its energy is actually constantly redshifting and can reach below 1.50 eV in our experiments. So actually this strong redshifting behavior indicates it's an interlayer exciton. So for an interlayer exciton, the electron and holes are basically seated in 2 different TMD layers. So it actually induces the out-of-plane dipole moment, and it will couple with the electric field to change its photon energy. So this so-called linear stock shift basically confirms this peak is coming from the interlayer exciton. And also interesting, when we apply the negative electric field pointing from the MoSe2 layer to the WS2 layer, then in our map, we do not observe this interlayer exciton. So basically, all these features are actually consistent with the band alignment transition in our TMD heterostructure. Basically, at zero or low electric field, our heterobilayer is actually a type 1 band alignment heterostructure. So both the conduction band minimum and valence band maximum are lying in the MoSe2 layer. And in this case, electron and holes will be confined in the MoSe2 layer, and they bound together to form this intralayer exton, which has no electric field dependence. But when we move to the positive gate voltage side, we have a positive electric field pointing from the WS2 layer to the MoSe2 layer. And now both the conduction band minimum and the valence band maximum of the WS2 layer is lowering. And above a certain threshold gate voltage, its conduction band minimum is even lower than that of the MoSe2 layer. So now the system becomes a type 2 band alignment system. And the electrons will relax to the conduction band minimum in the WS2 layer, and it bonds with the holes in the MoSe2 layer to form the interlayer exton, which is what we observed in our PL map that has a strong electric field dependence. And this band configuration also explains why we do not observe the interlayer exton on the negative electric field side, because in that case, both the conduction band minimum and the valence band maximum of the WS2 layer are moving up, and the system are still remaining in the type 1 band alignment. So the intralayer exton still dominates the entire PL map, and we do not observe the interlayer exton in that case. So we can further extract the dipole moment from our experiments and compare it with what we expect. So if we assume the electrons and holes that are generating the interlayer exton are sitting in the two TMD layers in our heterobilayer, then we expect the dipole moment of this interlayer exton to be about 0.6 electron charge times the nanometers. And then when we fit the slope of our linear stock shift of the interlayer exton in the PL map, we can directly get the dipole moment from our fitted slope, which is about 0.44 electron charge times nanometers in our experiments. And these two values are generally in agreement with each other. So basically, this means that the electron and holes that are generating this interlayer exton are indeed sitting in the two TMD layers in our heterobilayers. So basically, to summarize my talk today, I observe an interesting electric field tunable band alignment in molybdenum disulfide and tungsten disulfide heterobilayer. This actually allows us to controllably switch on and off the interlayer exton state. Basically, at zero or a low electric field, the system is a type 1 band alignment system. And we only observe the intralayer exton in the heterobilayer, and the interlayer exton state is off. And when we turn on the gate voltage and apply the electric field, the system becomes a type 2 band alignment system. And now the interlayer exton state is turned on. So this simple gate tunability of our heterostructure from type 1 to type 2 basically makes this heterobilayer very interesting in many potential applications. So with that, I'd like to end my talk today, and thank you for listening.